So now you can see the screen from Pajarito Powder. Barr, Zulevi, the CTO, he will bring the latest news of the comprehensive catalyst products for fuel cells and electrolyzers. Dear Barr, we are really happy to have you here. I know there was a lot of work and time together with CBMM you did, so the virtual stage is yours.
Hello, and thank you everyone for attending this Charles Hatchett Award webinar. In particular, I want to thank CBMM for inviting us and sponsoring this event. And of course, the folks at CBMM who are conducting this, as well as Better Technology that's hosting it with them. My name is Barr Zulevi. I'm CTO of Pajarito Powder, a comprehensive catalyst manufacturer for fuel cells and electrolyzers. As the previous speakers have indicated, we really are looking at a great growth in hydrogen demand over the next several years and decades. When we look at where that hydrogen demand increase is coming from, we see a range of markets. There's new feedstocks and existing feedstocks. There's building heat and power, residential and commercial, of course. Industrial energy, transportation, and power generation and buffering. Within these sectors, in particular, transportation takes up the largest chunk of energy demand and suggested hydrogen consumption. And this is the area that we as a company have focused on going into the hydrogen economy. Here is a summary of some of the potential that we see for niobium use in hydrogen mobility. We developed this case study along with CBMM, and it is based on some work that we did, partially sponsored by CBMM, as well as products that we've developed internally. When we do this, what we find is that looking at electrolyzers, which of course generate hydrogen, passenger vehicles, light trucks, and then heavy-duty trucks and buses, we can go ahead and estimate some of the projected usage of these cases over the next 20 years, as well as the power requirement and the amount of niobium that we know and have determined is necessary to achieve those. And we can now project somewhere like 0.5 ton a year of, 500 tons a year of niobium products in 2030. When we then look at the different cases of usage, we look at the hydrogen production sector, hydrogen delivery, and then the actual consumption. Right? In hydrogen production, we have electrolysis, which is the green way of producing hydrogen. And really, that's been our focus. And what we see here is somewhere around 200 times of niobium a year. There are, of course, opportunities in the transition economy. These are things like the existing steam methane reforming with carbon capture, steam methane reforming, and other approaches. In hydrogen delivery, what we need is an expanded network of piping and storage tanks to conduct hydrogen. This, of course, is also along the needs for high-pressure steels that are immune to hydrogen embrittlement, which is, of course, produces another sector with a great potential for niobium growth. And then, of course, transportation, which I just mentioned. I had really focused on the vehicle, the automotive sector, but of course, there are great applications in trains and ships, and of course, even airplanes. This is really a sector we don't know as much about beyond the automotive, but again, a huge range of niobium that's going to be needed within the next couple of decades. Other applications that some of the previous speakers have touched on, which we also think are of great interest, are things like ammonia production for fertilizers and potentially for energy transportation, steel production, which is a huge source of CO2 and of course of great interest, and then of course heat. Which is one of those applications that's even being implemented in the UK today. So all in all, what we see here is a really large increase in niobium usage due to the hydrogen economy. Okay, so a little bit more about Pajarito Powder. We are an 8-year-old startup. with established customers and qualifications. We focus on electrocatalysts for fuel cell and electrolyzers in the two electrocatalyst technologies of proton exchange, membrane, and alkaline. We have a range of intellectual property portfolios ranging from patents that we've licensed, patents that we've developed ourselves, and then proprietary and patented technology, including a manufacturing platform. Today, I'll show you a little bit about our product roadmap for electrocatalyst products, because one of the things we've learned really from most of our customers is that they're going to be developing these technologies over the next couple of decades. And so we really need to give them what they need today, tomorrow, and what they're going to need beyond that. We are supported by a world-class technical team and advisory board, and I think we have been able to really learn a lot about how to commercialize these new technologies through sales with major automotive OEMs and, of course, suppliers. Okay, so our manufacturing platform we've named the Veraform, and we use it to manufacture all our catalysts. I'll explain a little bit more about it next. So our major product is the fuel cell catalyst and support sector, where we make engineered catalyst supports that improve platinum utilization and durability and enhance catalyst performance. We also make a full version catalyst where we put platinum and alloys on those materials. Here's a bit of a roadmap off of our niobium containing materials. As you can see, we started deploying these in 2019. And over the next few years, we continue to work with existing customers and new customers to evaluate them and commercialize. You can see a whole list of applications here, but really the crux is that we are going to use the niobium to reduce the amount of platinum that's necessary to make fuel cells work by enhancing the intrinsic activity of the platinum, alloying or coating or so on, and by reducing the amount of platinum necessary because the platinum is stabilized by niobium-containing supports and structures. So I'll walk you a little bit through our fuel cell product. We make our carbon supports from the bottom up. We design them, which is an alternative to currently used commercial commodity carbons. We make our precursors and structuring agents, which include, of course, niobium. We mix them together in a proprietary approach, as I mentioned, using this Veraform platform. We graphitize them. We then end up with this engineered catalyst support that utilizes what we call the mesoporous effect that improves platinum effectiveness and allows high current density and improves stability. We can control some of the pore structures of this, which really help us there. You can see a mixture of small pores in the 7 nanometer range is when it's 20 and 30, and that's really the key to the performance improvement of these supports. And then, of course, in this latter stage, we can put platinum on there, which we can see here is really well distributed by this image here by the TEM in the top right. And then we can deploy these in a fuel cell in the bottom right of the image, and you can see really nice high performances. Okay, so let's look at these materials a little bit more closely. These engineered catalyst supports have this sponge-like or very Swiss cheese-like structure, and that's really unique to how they perform well. We're able to control the pore sizes, the surface areas, and the dopants of these, and that's what really gives them a unique performance advantage. When we look at some of the niobium doped supports that we made with support from CPMM, we see here in a Raman spectroscopy, the carbon structure doesn't really compare to the base materials. The X-ray fraction that gives you a measure of the crystallinity of the material is also not greatly affected, but you do see some variations depending on the structure and the amount and how the niobium is doped. If we look at nitrogen absorption, which we use to estimate and quantify the structure of the support, we can see here on the left a mix of pore sizes and pore volumes around the 5 to 8 nanometers that we can control. as well as surface areas ranging from 700 to over 900 square per gram, as well as our ability to change these larger pore diameters. This, of course, is analysis that comes from the right side of the nitrogen isotherms. So now that I've described a little bit that supports, let's look at the actual fully catalyzed systems. And here what we see is a full catalyst platinum on ECS as a baseline, as well as a platinum 9 niobium 1 alloy that we created with these materials. You can see here they're nicely distributed, 2.5 to 3 nanometer crystals. Okay. So in addition to the work we've done internally, including sponsored work with CDMM, we also have some government projects that both help defray our costs and help us work with some of the leaders in this field. One of these biggest projects is with the U.S. Department of Energy Hydrogen Fuel Cell Technology Office. And here we're working with General Motors, as well as 3M and Colorado School of Mines and Cornell to develop medium and heavy duty electrodes for fuel cell applications. Under this program, we are providing catalysts and working to qualify some who contain niobium. We are also working on the manufacturability aspect of these materials in another project that is led by Colorado School of Mines, has the University of Connecticut, Forge Nano, National Renewable Energy Laboratories, and the Fraunhofer Institute. Again, we're providing the catalysts, and analysis is by other folks. So now that we've spoken on the hydrogen use side of things, let's look at the hydrogen generation through electrolysis. Here's a roadmap, again, of where we think niobium can be useful in electrolysis. A range of both supports and activity enhancers. But again, our goal here is to reduce the amount of iridium and platinum needed. And doing so pretty much just like we did with the fuel cells, by enhancing the activity of iridium oxide and platinum, but also help stabilize it. Here are a couple of cases of demonstrations that we've had where we have an iridium niobium oxide material in the green line here that's being compared to the baseline oxide. This test was conducted by Proton On-Site NEL, who's the world's leader in electrolyzer. And what we see here is that an iridium oxide supported on niobium is able to achieve a better performance than a baseline iridium at a 40% reduction in iridium, which is a huge improvement. But more importantly, a 1,400-hour test of these materials under different operating conditions, including 2.3 amps per square centimeter at 80 degrees C for nearly 800 hours, shows stability. This is extremely exciting because this is the first demonstration in an actual cell of long-term niobium. And this really opens up the door for including niobium as a platinum reducer. So again, we're seeing the same performance compared to the baseline effectively, but at a 40% reduction in iridium, which is a great improvement. We're also looking at niobium-supported materials for a fuel cell electrolyzer combination called a reversible fuel cell or a unitized fuel cell. This approach is to use an electrolyzer to generate hydrogen when there's excess electricity in the grid, and then store that into the hydrogen, and then when electricity is needed again, use that hydrogen in a fuel cell and generate a renewable. And what we once again we see here an enhanced stability on these niobium-containing supports. So again, niobium can be used as an energy storage electrocatalyst. So, the previous speakers have also touched on this idea of an anion exchange or alkaline-based electrolyzer product. And this is something we have been working on and we think is extremely important. Certainly the results that have been shown on the niobium sulfide we think are excellent. This is a topic we work on and we continue to work on. Here we have a demonstration of a 900-hour test that we did in collaboration with Proton On-Site University of Washington, Washington University in St. Louis and Georgia Tech, showing that we can achieve a stable system using our catalysts. And we continue to work on these types of projects with Georgia Tech, Los Alamos National Laboratory, Lawrence Berkeley National Laboratory, and others, because we think that this anion exchange alkaline system is a really great potential product for the future, if for the reasons that it allows us to completely eliminate the platinum and iridium needed. So with that, I'd walk you a little bit through what we would need to do to take these very interesting products, right? These technologies that some of my previous, some of the colleagues and previous speakers have touched about, where they invent these extremely promising technologies in the laboratory. We take these technologies, we scale them up, we validate them in our hands, but then how do we take them and get them into customers' hands, right? Well, the next speaker, Shannon Knights, is from Ballard, who is one of the world's leaders in fuel cell systems. How do we take something from a lab scale and convert it to a bus that's driving around in your city? Well, I'm going to talk about a couple of cases where we have an existing customer that we've been working with who are now evaluating based products. So one of these is an electrolyzer manufacturer. They are mostly based in Europe and the US, but deploy products around the world. So we started out by essentially trying to provide them the next generation catalysts, right, which is what we have been working on. But they have also requested that we detune our catalysts and effectively provide them a drop-in replacement for their previous generation materials so that they can confirm our ability to manufacture at high quality. So they're qualifying us using the systems that they know. They're also qualifying improved versions of their current catalysts. And then in parallel, they're also working on what we have promoted as a niobium containing material because they trust us in the ability to manufacture a high quality product. And so what we see here is that to get niobium into a customer's hands will take some time and really depends a lot on the relationship between the raw material supplier, the manufacturers, and the end users. And I think that this is really a case where CBMM's outreach is really beneficial and is wise and will help grow the market for niobium hydrogen. So now that we've talked about hydrogen generation, let's talk about hydrogen use, right? We talked about automotive fuel cells, and that's what we're going to talk about right now. In this case, this is a major OEM in Asia that we have transitioned from selling primarily ECS, which, if you remember, those carbon-based materials, in competition with the commodity carbons that this OEM has been using now. And as we have transitioned from qualification to small level to now full systems, we've also been transitioning with them from just a carbon support, which is what they started out with, to a full catalyst system, which allows them to work faster. Again, having validated our ability to manufacture to their specifications. And now we continue to introduce things like niobium doped in the support, niobium as support, and the niobium-based alloys. So again, what we see here is that the people who are going to use this, the companies that are going to use niobium ultimately, need to really feel comfortable that the entire supply chain and manufacturing chain are reliable enough for them to build their company future on. And again, this is where CBMM outreach and stature have been extremely helpful. So I think that's really it for me. I wanted to thank everyone who has been paying attention. I want to ask for questions, and I want to thank, of course, CBMM, Beta Technologies, and to congratulate the Charles Hatchett awardee on their excellent work.